So joining us today is Božović, and he's going to be talking about Hikari Pool Party, which is related to the Spring framework used in Java. And currently he's a staff software engineer at Grid Dynamics and has a vast software engineering experience. So I'm just going to hand it over to Vuk, and let's give him a round of applause.
Thank you. I hope everybody is having a nice lunch and a good time here. So as my friend here introduced me and introduced my topic, saved me a few minutes. Unfortunately, there is no pool party, your typical ones, but we will be talking about something that everybody who used the Spring framework, either through Spring Data JPA, Spring Data JDBC, maybe practically anything that uses a data source has used. Now, this is me, if you haven't noticed. And what we will be talking about today is, first of all, we will be getting all on the same page regarding what's a connection, how we establish one. Then we will see what the Hikari Connection Pool offers us. We will then see how we can configure it, influence its behavior. Then we will run through some common issues which are faced in the real world. And then finally, we will maybe address the elephant in the room on how to exactly decide on the right number of connections for your database. Now, without any further delays, let's get back to the basics. So, as we all know, establishing a JDBC connection, it takes a while. So firstly, we have one round trip for the TCP connection. Then we have at least one round trip for a secure session. For example, TLS 1.2 may have just one round trip, but the principle stays. And then at the fourth round trip, we actually send what we want to query. Then we get the data back. And then we, again, spend some time destroying everything we painstakingly created. Now, we come to the question, what is connection pooling about? So there are some definitions on the internet. They are usually along the lines of amortizing costs of creating connections, which is fine, but that sounds like economics jargon to me, so I prefer to look at it in a different way. So it's paying when it's convenient for performance and paying only when necessary. Now, when is it convenient for us to pay? Well, application startups, we have different ways of deployments, zero downtimes, all that good stuff. So personally, I think that's the best way to pay up front. And when is it necessary? Well, usually in exceptional cases where connections need to be restarted, something goes wrong with the network or anything similar. Now, let's see what the connection pool has to offer us from a bird's eye perspective. So first of all, it offers us thread-safe access, meaning that every connection, once borrowed from the connection pool, will only be borrowed by one and only one user. User and thread in this context is a synonym, and I may use it interchangeably. And an important thing is that return connections are valid on a best effort basis. What does that mean? So immediately before the pool returns you the connection, it checks if the connection is valid. But as everything related to networking, there are no guarantees that in between the time the pool gives you the connection and you start using it, something won't go wrong. So again, it's on best effort basis. And it also offers some sane default values as to its behavior. The only two mandatory properties are, I think, JDBC URL and the driver name, driver class name, and that's about it. Everything else, you can use it without even thinking about it, or at least it will get you off the ground. One important thing it gives us is the prime directive, which states that users of the connection pool will only ever block on the connection pool itself. Why is that important? Because the pool then retains connection of how long you are waiting for a connection, instead of, for example, if it lets you create a connection, that means you're then being blocked on socket reads on the network. And that's outside of pool's control, and it cannot guarantee certain behaviors. Now, one also important thing is that waiting for a connection is busy waiting. Now, why is that important? Because when you have your typical blocked states in threads and everything, that means those threads are context switched out from execution, and thus all the pretty things with CPU caches get involved, wasting time, and completely, for example, the next thread that comes to execution may not operate within the same memory that the previous one did. That's why the pool is also very performant when measured in some metrics. Now, let's see, first of all, the design of this connection pool is very simple in its nature. You have about 5 or 6 parameters which you can modify in order to influence its behavior. Simplicity by design is something that I can agree with. The more complex something is, the more problems you have to solve, thus more options you need how to configure behavior. So one also good thing about the Hikari connection pool, in my opinion. So the first parameters are about, as you might imagine, controlling the amount of available connections to you. We have the maximum amount of connection and the minimum idle amount of connection. So the pool guarantees it will maintain a set of at least minimum idle amount of connections and will never cross the maximum pool size of connections. Now, throughout this presentation, I have experiments which I will introduce now, and we will look at the results of those experiments in the next slide. So, first of all, what's my test scenario? So it's slowly increasing demand up to 60 requests per minute towards my shitty application. Don't bother yourself with that. And the configuration is minimum 5 connections, maximum 10 connections. So let's see what the results give us. So the most important thing here is the bright yellow-green line. I don't know which color that is. That states how many total active connections are in the pool. So we can see in the beginning, as the demand builds up, 5 connections are enough to satisfy the demand. But as the request rate goes up, we see that the blue dotted line, which represents how many connections are currently active, is going wild. And there is this dark purple or whatever color that is down below, which is pending. Pending is the amount of users or threads waiting for a connection in the pool. So you can see that the rise in total connections is correlated with pending. Pending is the trigger for the pool to start asynchronously scaling connections up. So those are the basic and most obvious things that we can configure about the pool. Now, the next thing that we can configure is how we can retire idle connections, because since we have scaling, we definitely need to scale back down. That's done with the idle timeout. Now, it's just a time how long a connection can stay active without doing any work. Again, we have an experiment with 5 and 10, minimum and maximum pool size, and we have idle timeout of 30 seconds. Now, the experiment is a little bit different. We will still get up to 60 requests per second in demand, and then slowly drop off, and then see how the pool behaves. Now, as you can imagine, at the very beginning over there, there's a lot of blue dotted lines, meaning a lot of active connections, and we have pending driving it up to 10 connections immediately. Now, and then notice that after the beginning, there is no point where there are more than 8 connections in use. The pool figures that out. Some connections were not used, and then in bulk retires them, and we go to 8 connections. Then, as the demand drops, in my experiment, we have, again, a period where there is no more than 6 connections being in use. the pool also figures that out. After 30 or more seconds, we go back down to 5 connections in the pool. So the important thing here is how it is done. It's done asynchronously by the thing called the housekeeper task, which runs every 30 seconds, meaning that based on how the connections are in use, the idle timeout may be overstepped for some time, but it will eventually get, idle connections will eventually get retired. Now, the connection timeout is something that I was afraid of when I was a junior, because it's usually followed by exceptions and bad things and red text in Java. Now, as I grew up, I figured, well, that's not such a bad thing. Connection timeout is the amount of time you are willing to spend waiting for a connection from the connection pool. The experiment which we will look at is similar, but we will immediately build up to a lot of demand and then drop off to half of that demand and then until the end of the test. Now, I have only 3 connections in the connection pool and a connection timeout of 5 seconds. The results may not shock you, but as we can see, as the demand builds up, so do the response time. So the left axis is response time in seconds, and the bottom axis is time from the start of the experiment. So as we can see, the demand builds up, the pool is able to keep up with demand for a while. Then we have these red dotted lines, which are our connection timeout exceptions. And we can see, importantly, that our response times are capped at 5 seconds. So that's the part which I am interested in. Sometimes it's a lot better to let your users go back to whatever they were doing with an exception, saying come back later, instead of having them wait forever. We all know what happens then. Refresh button gets spammed and nothing really good comes out of that. And then as the demand drops off near the end of the experiment, we can see also that the amount of exceptions also starts dropping, but is never 0. So it is possible that even if you have sufficient demand, some threads may get starved out because the pool does not save the order in which requests for connections were made. Again, for simplicity's sake and for performance. Now, one thing that insurance companies and thread pools have in common is mass extinction events. So, in the context of insurance companies, they lose money. We, in the context of thread pools, lose performance. So, first of all, where can we find these mass extinction events? Usually, we can find them in the network, on database side. For example, some routers, somebody get burned out, somebody steals a router. Databases may be configured to close connections which were not used for a period of time, thus closing in bulk some connections which we are relying on, but turns out, okay, they're not valid. So, but the thing here is we cannot influence this. So in order to combat this, the connection pool has one parameter, but actually first let's look at a test, how they manifest themselves. So we will have 5 connections, and at one moment I will close forcefully 3 out of 5 connections, leaving us with only 2 connections. This experiment consists of 2 stages. The first half of the graph is our baseline. That's what the demand looks like without closing any connections. The right part is, as you might imagine, the big spike is what happens when the connections are, 3 connections are extinct. Some kind of time that accumulates while there aren't enough connections, forcing all other response times to go up. You can also look at this right graph. The first column is average response times without closing connections, so they are around 100 milliseconds. And with closing connections, we can see it's above 400. So this is how we can spot mass extinction events in the wild. Usually they are spikes which refuse to go down without sufficient demand lowering. In order to combat this, there is the maximum lifetime parameter. You set it to a certain amount of time after which every connection will be closed and then a new one will be opened instead. So what's the test for this? Well, let's just start the application and leave it alone. Maximum lifetime here is 30 seconds, and there will be 20 connections in the pool. This graph shows only the amount of connections present in the pool. So from reading it from left to right, we can see that immediately on startup, connections are growing to their maximum size. And then we have some stormy period where connections are being reset. Then we have some calm period. Then again a stormy period, then a calm period. So what's happening here? In order to prevent the pool from mass extincting itself by closing all the connections at the same time, because think about it, we gave it a single value. So the time it was created plus that time is the time when it should be closed. And then since if connection opening time is sufficiently short, everything closes within a second, thus creating a mass extinction event itself. So what the pool does is gives you a 2.5% variance on the maximum lifetime value, meaning it spreads that interval where connections are closed out. And as you can see, we are never left with less than 17 active connections, or idle connections in our case, while they are being recycled. I would say that's a pretty good design. The last parameter, which is nothing special, is the keep alive. Practically what it does is it reserves a connection from the pool, pings it, executes a query, or calls the JDBC4 is valid API, thus informing the database server on the other side, the connection is alive, don't do anything with it. Now, we move on to some common issues. So, during my junior days, a lot of the time, performance issues I solved, for example, let's just raise the connection pool size, and that will fix it. Now, in the words of the creators of the pool, and from my experience, just adding connections to the pool will not solve anything. The pool is the last place that will give you performance problems. Now, we will demonstrate that. But first, let's demonstrate a problem where increasing the amount of connections will actually help you. And that has to do with network. So I ran an experiment where I had my JMeter run from my bedroom apartment, targeting a RDS instance in AWS somewhere in Indonesia, I think. It took 21 network hops to get to the database. The second experiment was me starting an EC2 container in the same zone on AWS, which only had one network hop to the database. AWS isn't lying when they're organizing your resources into network groups. And what we have here is practically my bedroom setup achieves the same throughput as the EC2 setup with 6 connections, what it takes the EC2 instance 2 connections to achieve. And you can see as the number of connections grow, the throughput of the application in the cloud does not really change that much. While my bedroom case manages only to catch up at 6. So network latency is something that impacts how efficient connections are. You can look at it that. So this is one case where increasing the amount of connections is actually solving a problem. Now, let's take a look at another example. So commonly, what we have in our applications is that, well, some queries are extremely fast, some queries take forever to execute. Now, for whichever reason that may be. But in my case here, my cheap queries, as I like to call them, are executing in the range of tens of milliseconds, while my expensive queries are executing in the range of tens of seconds. So it's orders of magnitude difference. And the ratio between these are 1,800 cheap queries to 50 expensive queries. This red color indicates something. First of all, response times, note that they are in seconds, even though the cheap queries are executing in tens of milliseconds. Why? Well, because our expensive queries are holding the connections hostage, if you will, and only releasing them after a certain amount of time, thus driving the response times of even the cheap queries up to heights. And as you can also see, this red line is the error percent. So in one case, 80% error rate, meaning connection timeout, which is set to 2 minutes. So this is not really something which we would be happy with. Now, instead of raising the amount of connections, let's think resiliently. Let's define 2 data sources. We will have, with the same amount of connections, we have cheap data source with 2 connections, and we have the expensive data source with 3 connections. So it's still 5, like we had in the previous case. That yields us going back to the response times in milliseconds for cheap queries. So at around 100 milliseconds, 150 average. Thus, a part of our application is still usable, even though we have slow parts in it. Now, the slow part isn't really much improved, because it doesn't matter how you configure the connection pool, slow running or badly designed queries are going to be consuming all the connections that you have. So the story here does not improve, other than, well, the rest of the system is usable. Now, one more example that we will have is, for example, with cluster databases. So in AWS, you have the Aurora database, which essentially has one master replica, which is responsible for writing and reading. And then you have a bunch of replica reader instances, which are only responsible for reading or running select queries. Now, how you connect to those reader instances is through some kind of timed DNS switch, meaning the URL at one moment points to the first replica, at another to the second, at another to the third. Now, this may seem like an elegant solution, but it creates some problems for us. So let's run it with an experiment. We have a maximum lifetime of a minute, and we have 10 connections. And what I didn't mention here is I have 5 instances of this application running. Let's look at, this is taken straight from Amazon's analytics dashboards. These are displaying how many active connections does one reader instance have. As you can see, this graph, there are a lot of spikes in it. For example, there is one moment where reader 1 has around 30 connections, while reader 2 has closer to 10 connections. The picture doesn't improve much when reader 3 comes online. It then takes half of the connections, while reader 1 and 2 have around 10 connections. So this uneven distribution of connections will eventually lead to uneven usage of resources, meaning more money to Amazon, and nobody likes that. How this was solved is that somebody was annoyed enough by this, that the fact this happens, and they created their own JDBC connector, which is called the Dice Fairlink connector, which bypasses completely the DNS part and distributes connections on a round-robin basis. You can see that now it's much more closer. At the beginning, reader 1 and reader 2 are within a few connections of each other, thus utilizing both instances evenly. And even when reader 3 and reader 4 come online, again, they are even closer within a few connections of each other. So this QR code will lead you to the, I think, the discussion on GitHub, on Hikari GitHub repo with the issue still open. Now, finally, we get to attempt to address the elephant in the room, but not before we talk about some of the basics. Well, what is actually a database? When you think about it, when you look at a database through a microscope, it's practically a collection of finite resources. Finite resources which are competed for by whom? By other CPUs in the world via network. Now, if we also remember computer science basics, how you deal with concurrency is, well, you have certain locking mechanisms which then put threads to sleep, do a lot of things, and practically when you have a lot of CPUs through network competing for different threads on a processor, which is competing for memory, for cache, for disk, you get the idea. There's a lot of locking and synchronization that needs to happen. So the final experiment of this talk is done not by me, but by the organization called the Real World Performance Group. They are a part of Oracle. And on this QR code, you can find a magnificent 144p YouTube video, which runs Windows XP. And they are running a simulation of 9,600 users making a gaming transaction, whatever that is, every half a second. So in my previous experiments, we had 60 requests per second. These guys have 16,000 requests per second on a 12-core CPU system. So the first experiment was done with 2,048 connections. Now, the response times here were 100 milliseconds. Now, please raise your hand if you look at 100 millisecond response times and think that this needs to be fixed. Nobody, okay. Agree. I agree with you. So 40 milliseconds were spent waiting for a connection, 70 milliseconds were spent executing the query. CPU usage was around 90%, and there were a lot of wait events, synchronizing on database transactions, updating indexes, whatever. They did the unthinkable. They reduced the amount of connections to 96 connections. The response times were an order of magnitude better, 3 milliseconds, with 1 millisecond spent waiting for a connection, 2 spent on executing the query. And the important thing was that wait events were gone, meaning that our application was now CPU bound, thus improving scalability infinitely, and which leads me to my final point. Just throwing connections to the database will not improve performance. It will accomplish the exact opposite. Thank you. Questions?
Thank you for this awesome talk. We have time for one question. Anybody wants to raise any hands?
No need.
Yeah, actually, there's one question from Vova, which asks, which tool did you use to measure the connection pools and stuff and graphs?
It's JMeter for running requests, and it's Grafana plus essentially it's open telemetry with Grafana and Prometheus for scraping. You can literally ask ChatGPT, it will set everything up correctly through Docker.
Cool. Sorry, we're kind of out of time, but Vuk is going to be here around the conference, so let's give a round of applause for him, and that's it. Thank you very much.